Hey, grade 7s, we're going to look at 7.1 classifying figures. Today we're going to learn about how to identify, describe, and classify geometric figures, and of course we're going to find and destroy Waldo. Let's go right off to this. A polygon is three criteria that we need to meet. We're talking about simple polygons today, and the first one is that it's a closed figure with sides that are line segments. So this is a closed figure because it has, it's not open, as another way of looking at it. This beautiful egg is also a polygon. This one is not a polygon. You can see that this little line segment right here, it ends, it doesn't join back to it, so it's not a closed figure. Exactly two sides meet at a vertex. Our vertexes are all the corners, right? If you take a look at the corners of this pentagon, you see that, there's a lovely polygon there. It has 5 sides, and because each little corner only has 2 lines that meet up at the same point, that makes it a polygon. This one as well, if you look here, there's one line and there's a second line. Every single corner is the sum of 2 lines, or 2 lines meeting. But in this one, it's not. You got one line this way, a second line that way, a third line this way, and a fourth line here. This is not a polygon. This one, sides intersect only at the vertices or the endpoints. The line segments are always joined. Right off the bat, this big circle, it's not even a straight line, so this is not a polygon. Are the segments always joined? Or the endpoints of segments? Here, let's take a look at this line segment right here. There's an endpoint right there, and that is joined to this one. There's an endpoint right here, and that's joined to this one. Take a look here at this triangle with a rat tail. This line segment right here is joined to this one, but this one has this endpoint right there, which is not joined to anything, so therefore it is not a polygon. So we got some polygons over here. These are all polygons. They're all closed shapes. Vertices is met by 2 line segments, and each line segment has an endpoint that is joined to the rest of the polygon. These ones are not. You got the rat tail, you got a circle, you got this funky oval, you got the, there's actually a name for this one, but we're not going to go into that. It's a very complicated kind of polygon. Why is this one not a polygon? I mean, I see a vertex with 2 with 2 line segments. It's joined. A second vertex right here, 2 line segments that join. It's closed. It looks really good. The problem is there's one little detail here, that this ain't no line segment. It's not a straight line. It's a curve. So anytime you see a curve, it is not a simple polygon. Then we get to a little more complicated. We get regular polygons and irregular polygons. There's sort of a subclass of polygons. The regular polygons have all sides are equal and all angles are equal. So this is a regular pentagon, penta meaning 5, and it's 108 degrees every single angle, all within it. A rectangle, let's take a look at this one. Why is this rectangle not a regular polygon? It's an irregular polygon. Well, it has all the angles are the same, right? They're all 90 degrees. So it satisfies that criteria. The problem is this line and this line, while they may be equal, obviously they are not equal to this line or that line segment. That's why it's an irregular polygon. Regular polygons have line symmetry. These are really cool. It means like how many times can you fold this thing in half so that one half touches the other side? And let me sort of make this a little simpler. If I asked you to do a little origami with this beautiful hexagon, and I said I want you to fold it in half so that, let's say, this point right here touches this point perfectly, you would fold it along the middle. Well, you could also fold it this way, and this side right here would touch right over there. So this is so far 2 lines of symmetry. There's a third line, a fourth, and a fifth, and a sixth. So what's interesting, a 6-sided regular polygon has 6 lines of symmetry. Why does this polygon not have line symmetry? Well, any way you slice it, there is no way of cutting this thing in half and folding it so that each side touches perfectly. If I folded this, you're going to have this little piece that sticks up like that. It's not going to look very nice. Regular polygons also have rotational symmetry. So we'll start off with this hexagon right here. What this means is, as I rotate it, it will come back onto itself. And it's easier to show you than to describe that. So we started right here. I rotate it, and watch what happens. I can put it back on, and it meets up perfectly with the, well, almost perfectly. It's my drawing that's not perfect. I can rotate it again a second time. I can rotate it a third time. Now you're probably jumping ahead and thinking, okay, monsieur, it's a hexagon. So it probably, and has 6 sides, and therefore I bet it's got rotational symmetry of the order 6, meaning that I can rotate this 6 times and it will land on itself exactly 6 times. There you go. There's the 6th time. Now, even though this isn't a regular polygon, because the angles aren't all the same, nor are the sides the same, let's try rotating this and see what happens. Will it come back onto itself? So far it's not, definitely not, no, 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 no. It does not rotate back onto itself. I had to do a full 360 turn, so that one does not have rotational symmetry. This one right here, this sort of diamond, big diamond shape, let's rotate this one and see what happens. Once I go a half rotation, aha, it does actually go back on itself. Once. Only once though. No other time does the black line overlap the blue. So this is a rotational symmetry of 1. This one has 6. This one has 0, no line rotational symmetry. And this one has order 1. So we're looking at relationships, and I think you're probably figuring this out already, that if you've got a regular polygon like an equilateral triangle, it's going to have rotational symmetry. Well, first of all, it has 3 sides. It's going to have rotational symmetry of 3. It's also going to have line symmetry of 3. So there's some kind of relationship going on there. I bet you can figure that out. Let's see. Forget that. All right. There's 2 more subdivisions here. There's convex polygons and concave polygons. So a convex polygon, all of the interior angles are less than 180 each. So this looks like an equilateral triangle. So that would be 60 degrees right there. And this one right here is also 60, and this is also 60. None of the angles are more than 180 degrees. In this one, even in this one, this looks like about 108. I know it's 108. But it looks like it's much larger than the 60, but it's still less than 180. And this is where we get to the concave polygons. Concave polygons have some angles that are less than 180. Like that looks like about 30. This looks like about 50. This is about 110. This is about 130, 140. And this is about a 98 or something like that. But then it's got this one right here, this huge one. And we can just sort of look at this. We can sort of, that looks like about a 60, so this is about a 300. If you wanted a little trick to remember this, bats live in caves. So I'm just going to correct this because it's not convex, it's concave. Concave. Bats live in caves. And so you draw the Batman symbol, and everywhere you see a little red dot, those are all concave. It's concave because those angles are all bigger than 180. Every single one of those little dots. You know what? I think that's all we're going to do. All right, guys. Hope that helped. Bye-bye.